Hello, everyone. So last time we finished the topic of L'Hopital's rule. Now today we want to study a new topic called mean value theorem. So basically Rolle's theorem and mean value theorem. So let me explain about the goal first. What is our goal in this topic? So let's say we have a differentiable function because you know the topic related to derivatives. So we need to have a differentiable function given a differentiable function f of x. Our goal is we want to find the solutions, or let me say we want to find out about the existence of the solutions for f prime of x equals 0 or f prime of x equals a f prime of x is equal constant. And in particular, f prime of x equals 0. See, always finding roots of a function is an important topic or problem in mathematics. But if f of x is a function, then f prime of x itself is also a function. So solving for f prime of x equals 0 or finding roots of f prime of x is important by its own, because first of all, f prime of x is a function itself. And moreover, even if we think about f of original function f of x, we know that f prime of x equals 0 gives us the points where the tangent lines are horizontal. So, i.e. roots of f prime of x, i.e. the points with horizontal tangent lines.
These ones have been made into long square posts. I wonder how Farmer Tom and Liz are getting on.
Okay, so points with horizontal tangent line. Sometimes we're interested in finding such points, or sometimes we want to, let's say we have a function, given function, we want to find the roots of a given function. So if that function happens to be a derivative of another function, well, again, we can apply this concept, because this concept helps us to at least show the existence of roots of f prime of x equals a constant, and in particular f prime of x equals 0. So roots of f prime of x.
I hope you have enjoyed.
Okay, so let's start with Rolle's theorem.
See you again soon. Bye.
Which is a particular case for mean value theorem. So let me first state the Rolle's theorem. Let f of x be a function let f of x be a function that is continuous on some closed interval, let's say a to b, and differentiable on open interval a to b. And suppose that f of a equals f of b, then there exists C between A to B such that f prime of C is equal to 0. Let me sketch the graph for you. See, the theorem says, this theorem called Rolle's theorem, says that if you have a function where f defined on an interval which is differentiable. So first of all, you may ask, why did I mention differentiability and continuity separately here? Because we know that differentiability implies continuity. So why do you think we have to mention them separately? So can't we say that if a function is differentiable, then it's automatically continuous? Well, at a given point, yes. At a given point, if the function is differentiable, then it's continuous. But differentiability is defined on open interval. So I can require differentiability on open interval A to B. But then what about at A and B? So between A to B, the function is differentiable implies continuity automatically. But what about the endpoints? At the endpoints, because this condition is given on an open interval, doesn't imply anything about continuity, but I mean, on the open interval, differentiability implies continuity, but this is, the endpoints are not included here. So that's why I have to require continuity separately for the endpoints. Okay, so that's why we say continuous on the closed interval A to B in order to ensure continuity, right continuity, because if you remember, continuity on the closed interval A to B means right continuous at A, left continuous at B. So this guarantees right continuity at A, left continuity at B. And between A to B, the function is differentiable, so it's also continuous, definitely. Right continuous at A, left continuous at B, and differentiable, and of course, continuous between A to B. So the reason that we state this sentence separate from this sentence is to ensure right continuity at A and left continuity at B, which is not implied by the second condition. So we have a function which is differentiable between A to B, and f of A is also equal to f of B, which means the f of endpoints are the same, which means the function has the same height at the endpoints. So let's say this is A and this is f of A. Then it will have the same height at B. So the height is the same because f of A represents the output or the y value or the height of the function at A. The height of the function at A and B are the same. And then if we can conclude that the function, the derivative of the function will be 0 at some point in between. Derivative equals 0 means the function will have a horizontal tangent line. So intuitively from the graph, we can say that if the function, if you start from some point and then you have to come back to that point again, right? Because we are supposed to have the same height at the end of that interval. So we start from some height, we have to come back to that height again. So if you start from some height and you have to come back to the same height, then we need to have a peak, right? Like a maximum or a minimum, because we can also come back to the height. We can go up and down or go down and up, or we can just stay the same. You know, there's also an option, just stay in the same height for the whole time. But in any case, whether this or this or this, you will have a horizontal tangent line, whether you have a maximum like this picture or a minimum like this picture, or just you have a constant function like this picture, you will have a horizontal tangent line. So horizontal tangent line, obviously here at the maximum, here at the minimum, and here at all points, basically between A to B, you have horizontal tangent lines. So of course, this is not the proof, but just an intuitive motivational reasoning that if you start from a height, you go back to the same height, then you have to go up and down or down and up or just stay the same height. In any case, you will have a horizontal tangent line. Therefore, the derivative will be equal to 0 at some point C. So the point C here in this picture is basically here. This is C, and f prime of C is equal to 0. F of C is not 0, of course. F of C is this height here, which is of course not 0. It could be 0, it doesn't have to be 0. This picture is not 0, but f prime of C is 0 because you have a horizontal tangent line at this point. Okay, so we are not going to prove this theorem. The proof will be given in an analysis course. So if you're interested in the proof, you can take in Math 225 Analysis 1. If you take that course, you will see the proof of this theorem. Okay, so your job in this course is not to learn the proof, but to learn the theorem and what the theorem says, the concept of theorem, the intuition behind the theorem, or the graph related to this theorem, and also, of course, some examples. And also, maybe regarding the proof, you are not required to prove this theorem itself, but we could prove some theorems, some other theorems using these. Or some results at least. So I'll try to give some examples. Okay, but anyways, you are not required to know or learn the proof of Rolle's theorem in this course. So let's look at an example. Let's start with a simple example that f of x equals, let's say, just x squared plus 5. On the interval -2 to 2, show that the conditions of Rolle's theorem hold and find the value of C. So here f of x is a polynomial, which is because conditions of the theorem say requires continuity on the closed interval, differentiability on the open interval. But here we have a polynomial which is differentiable and of course continuous everywhere. So we have no problem with that. So solution, f of x is a polynomial. So we can say it is differentiable and therefore continuous.
The children have enjoyed seeing the lamp. And there's another long day.
And continuous everywhere.
Farmer Tom has finished his work.
What is the other condition? F of A must be equal to F of B. So also F of -2 is equal to F of 2, which is 9. And therefore that means F prime of C. So we can, thus the conditions hold. And we can apply Rolle's theorem. So f prime of c equals 0. That gives f prime of x is 2x. So f prime of c will be 2c equals 0. And that gives c equals 0. And and c equals 0 is between -2 to 2. So the Rolle's theorem guarantees the existence of a value of c between -2 and 2 with f prime of c equals 0. Well, f prime of c is 2c. 2c is equal to 0 at c equals 0. And of course, c equals 0 is between -2 and 2. So yeah, it's just an example of Rolle's theorem. Existence of c is guaranteed, and as expected, we have a value of c between -2 and 2. In this case, it's 0. So in this case, c is right in between, in the middle, between -2 and 2. But that's not always the case. It doesn't have to be the case. Okay, in this example, so when we say there is a c between a to b, we don't mean right in middle, okay? Could be towards a, more towards a, more towards b. It could be right in the middle. In this example, it's right in the middle, but it doesn't have to be right in the middle. I'll give an example where c is not necessarily right in the middle. Okay, so the next example, let f of x equals, let's say x squared for x less than equal to 0, x cubed for x bigger than 0. On the interval, let's say -2 and cube root 4. Again, show that the conditions of Rolle's theorem hold, and find the value of c. Okay, so again, well, here we have a piecewise function, of course, and each piece is a polynomial, and we know again each polynomial is continuous and differentiable everywhere. But then at the border point, we have to check the differentiability. I mean, continuity and differentiability, but once we check differentiability, of course, it implies continuity. So to check the differentiability, we need to check the border point, which is x equals 0 here. The solution, if let's say x equals a not equal to 0, then f of x is differentiable at a, since polynomials are differentiable everywhere. Now it remains to check at x equals 0. At x equals 0, first we can check the continuity. The left limit and right limit are 0. Left limit means limit x squared, right? And the right limit is also 0. Because limit x cubed is also 0. And therefore, this means the whole limit is also 0, which is same as the value of f of 0. Okay. And so we have no problem at x equals 0 in regarding continuity. Now for differentiability, so f of x is continuous at x equals 0. for differentiability. What do we need to check? We need to check limit f of x minus f of 0 over x minus 0, x approaches to 0. F of 0 is 0, so again, you have to check the right limit and left limit and see whether they exist. So for right limit, now if x is bigger than 0, then I have to use which function? I have to use x cubed. So limit x cubed minus 0 over x minus 0, x approaches to 0. And then this is limit x squared, x approaches to 0 from right, and that's 0. And for the left limit, we have to check limit x squared minus 0 over x minus 0, x approaches to 0 from left. And that's limit x as x approaches to 0 from left, which is 0. So left limit, right limit, they are both 0. So that means the whole limit is 0. So limit f of x minus f of 0 over x minus 0, x approaches to 0, exists and is 0. So that means f of x is differentiable at x equals 0 and f prime of 0 is equal to 0. Okay, so we check the differentiability, the condition for differentiability of f on our interval a to b. And of course, it's continuous on the closed interval as well. So the conditions of the theorem will hold. The only thing that we still need to check is f of a equals f of b. Now for f of a equals f of b, I can say f of x is continuous on minus 2 cube root 4, and f of x is differentiable on this interval, open interval. And for checking f of a equals f of b, this is very easy to do. F of a is how much? F of minus 2 is minus 2 the whole squared, which is 4. F of 2 is cube root 4 the whole cube, which is 4. Well, that's it. So f of cube root 4. So f of a, f of minus 2 equals f of cube root 4. And so by Rolle's theorem, what can we conclude by Rolle's theorem? There must exist C between minus 2 to cube root 4 such that f prime of C is equal to 0. Well, we just checked here that f prime of 0 is 0. So our C value that we are looking for and guaranteed by Rolle's theorem is basically C equals 0, because f prime of 0 is 0. So we are looking for a value of C with f prime of C equals 0. So we can set C to be 0. So we saw above that f prime of 0 equals 0. So that means we can set C equals 0. Then f prime of C will be 0. So the only thing I want you to note here, unlike previous example, C C, the value of C in this example, the value of C is not in the middle of the given interval. See, previous example, the interval was -2 to 2. Here. The interval is -2 to 2. The middle of the interval -2 to 2 is 0. And C was 0. In this example, the interval is -2 and cube root 4. What will be the middle of the interval here? If you have an interval A to B, the middle of the interval will be the average of those numbers, A plus B over 2, right? So the middle of the interval here would be -2 plus cube root 4, the whole thing over 2, which is some number, but that number will not be 0. It's just a number between these two numbers, -2 and cube root 4, but it's not 0. But the value of C here is 0. So that means the value of C in this example is not in the middle of the interval, because the middle of the interval is some number other than 0. All right. So now let's look at the mean value theorem. So again, suppose that f of x is a continuous function on the interval a to b, and f of x is differentiable on the open interval a to b. Then again, we can say there exists C between a to b such that f prime of C is equal to f of b minus f of a over b minus a. In particular, if f of a equals f of b, then f prime of C is equal to 0, as predicted by Rolle's theorem. See the theorem, the first condition is same as what we had for Rolle's theorem. We have a continuous function on the closed interval and differentiable on the open interval. We do not have the condition of f of a equals f of b here anymore. But here we can say that f prime of C is equal to f of b minus f of a over b minus a. Now, if f of a happens to be equal f of b, then right-hand side will be 0, and therefore left-hand side must be 0 as well, which means f prime of C must be 0, which is what we had in the Rolle's theorem. So we can say Rolle's theorem is a special case of mean value theorem. Because if f of a equals f of b in Rolle's theorem, we were assuming f of a equals f of b. But if f of a equals f of b, then f prime of C will be 0, because right-hand side will become 0. Now, the question here is, I remember I was learning this in undergraduate studies, so I was asking myself that, well, if this is if Rolle's theorem is a special case of mean value theorem, why do we emphasize on Rolle's theorem and give it a separate name? Well, we have the mean value theorem, and that's just a special case. So we could say just a special case of mean value theorem, or we could say a corollary of mean value theorem. Why do we emphasize on it so much and give it a separate name? Well, the answer is yes. This seems to be, it seems that Rolle's theorem is a corollary or conclusion of mean value theorem. This is how it looks in the beginning. But it's actually the opposite, the other way around. Mean value theorem is a corollary or conclusion of Rolle's theorem. So when in analysis course, when you want to, prove things in the right order, first we prove the Rolle's theorem. Then using the Rolle's theorem, we can prove mean value theorem. So this shows the significance of Rolle's theorem, because although it seems to be just a special case of mean value theorem, but no, it's the significance is beyond that. Once we prove Rolle's theorem, we can prove mean value theorem using Rolle's theorem. You may wonder how, because in Rolle's theorem we need to have f of a equals f of b, but in mean value theorem we don't have such requirements. But that's true, and that's why the proof is a little bit tricky. But still is doable. We just need to define another function, let's say h of x, where h of a equals h of b. And then for that function, we can conclude h prime of c equals 0. And once we write that down, then we'll see that h prime of c equals 0. It turns out to be equivalent with f prime of c equals this expression. Okay, so Rolle's theorem is important because we can prove mean value theorem using Rolle's theorem. Now I explained Rolle's theorem graphically. Graphically, we said Rolle's theorem is, if you have a function which has the same height in the beginning at the end, then you go up and come down, or you go down and come up, and then anyways, you'll have a maximum or minimum, or you have a constant function. In any case, you have a point with horizontal tangent line. What about this case? In this case, f prime of c is not 0 necessarily, so we cannot say that we have a horizontal tangent line at c, at the point c, necessarily. But how can we interpret it? So right-hand side is not 0, but right-hand side should be familiar for you. F of b minus f of a over b minus a. That means delta y over delta x, rising y over rising x. That's the slope of secant line connecting a and b. So f prime of c is equal to the slope of the secant line connecting a and b, which means, and f prime of c is the slope of tangent line. So slope of tangent line at c equals slope of secant line connecting a and b. And slope of two lines being equal each other means two lines are parallel to each other. So there is a point between a to b where the tangent line at that point is parallel to the secant line connecting the endpoints, because this is the slope of, right-hand side is the slope of secant line connecting the endpoint, which happens to be equal to slope of tangent line at C. And slope of two lines equal means those two lines must be parallel. So the tangent line at some point C must be parallel to the secant line connecting the endpoints of that graph. So let me sketch the graph for you. See, we have a function which is continuous and differentiable, but then f of a doesn't have to be equal to f of b anymore. So just a function which is continuous and differentiable, so which means no gap, no break, no sharp point. So here we have a, and here we have b, and then here is f of a. Here you have f of b. And then you have a line connecting these 2 points. Okay, this is the line, secant line connecting the endpoints with the slope f of b minus f of a over b minus a. So this must be parallel to one of the tangent lines. In this graph, well, basically it will be a line like this, somewhere around here. So C, and the slope equals m equals f prime of C, the tangent line at x equals C is parallel to the secant line connecting the endpoints. Okay, so this is the interpretation of mean value theorem. If the function is continuous on the closed interval, differentiable on the open interval, then at least at some point C between A and B, the tangent line at that point will be parallel to the secant line connecting the endpoints of that graph. And as you can see there, we can interpret basically Rolle's theorem as a special case of what I said, that, but in Rolle's theorem, the line connecting the endpoints of the graph will be a horizontal line because the function is supposed to have the same height at the endpoints. So a line parallel to a secant line, a tangent line parallel to the secant line connecting the endpoints means a tangent line which is horizontal, because the secant line itself is horizontal, and something parallel to horizontal must be horizontal. So that's why we said that in Rolle's theorem, we need to have a tangent line which is horizontal. Okay, so this is the theorem and the interpretation and the graph and the intuition. And then for the proof of mean value theorem, as I said, it can be proved using the Rolle's theorem, but will be done using Rolle's theorem. We will see again in Math 225. Okay, so again, for this course, we don't require it. You don't require the proof of mean value theorem, but I just want you to know that it can be done using Rolle's theorem. And some trick, of course, because Rolle's theorem, as I said, in Rolle's theorem, you need to have a function where it's f of a equals f of b, but in this case, we don't have f of a equals f of b necessarily. But we can, with a small trick, you can define a function h, where h of a equals h of b, and then h prime of c equals 0 will imply what you need to show, which is this expression f prime of c equals f of b minus f of a over b minus a. Okay, guys, now let's look at some examples and some corollaries or conclusions of mean value theorem.